picking up on example 11 on page 439, second half of section 7.4. In this lesson, you are going to feel like they are throwing 50 formulas at you. And that's basically what they're doing. It's not quite 50. But they go through and they are giving you a derivative and an integration formula for all different types of logarithmics and exponentials and that type of thing. So the first page of your test is going to be matching formulas. Make sure that that is free, easy points for you. Go ahead and start making flashcards now of the formulas because that first page, a big bulk of matching formulas. Okay, so example number 11, they ask me to integrate tangent x dx. All right, if we do u substitution, like we let u be equal to tangent, we don't have its derivative sitting there. So I can't do u substitutions. The only other thing that I could think of would be to rewrite tangent as sine over cosine. So then I can do some u substitution, right? So what do you think you want to use for u? A little bit of trial and error. What do you want to use for u? Okay, if I let u be equal to sine, then its derivative cosine is sitting there, but the problem is its derivative is in the denominator, and if I'm going to replace that differential, I would need it in the numerator, right?
Wait, can we change the tangent?
All right, so what if we let u be equal to cosine? Okay, if we let u be equal to cosine, what's its derivative?
Negative sine.
Negative sine. All right, so let's try that because the sine is in the top already where we need it. So again, that idea of you might need to try it a couple of different ways, or if you think it through a little bit, you might save yourself some time and energy. So if u is equal to cosine, you told me that the derivative would be negative sine, so the differential would be negative sine dx. I just have sine x dx, so what do I need to do? Yeah, divide out the negative. So we can say negative du would be sine x dx. So let's come over here. We'll replace sine x dx with a negative du, and then our cosine is just u. All right, we've already learned the integration formula for 1 over u. It's ln absolute value of u, and we already had that negative out in front. We were the ones who did the u substitution, so we need to back substitute. So let's put the cosine x back in for u. Now, when we did a problem like this before with the absolute value, we were able to drop the absolute value signs. I think we had something like absolute value of x squared plus 1. And there was no way that could ever be negative, so we didn't need the absolute value signs. Do you need the absolute value signs for cosine? Can it ever be negative? Yes, so we do need those there. Remember our logarithmic properties, that if you have a negative in front of a logarithm, or if you have any number in front of a logarithm, that it can be moved to be the constant or the exponent of that log. And if you have an exponent on a logarithm, you can move it out in front and make it the constant. So let's do that. Let's move that negative to make it an exponent. Cosine to the negative 1 is 1 over cosine. And by definition, 1 over cosine is secant, right? So we could simplify that to ln absolute value secant x plus c. And we actually just proved the integration of tangent formula that they give me on page 439. So we discovered it before they gave it to us. And that could also be considered a proof of it. So integration of tangent is going to be the natural log of the absolute value of secant x plus c. All right, then they also give me the derivative of a general logarithm. So we're saying log base a, not ln, but log base a, where you could have a log of 2, a log base 2, log base 10, log base 27, whatever you want. So if I have the derivative of log base a of x, they tell me it's going to be 1 over x ln a. So if I didn't have just a plain x there, if I had a quantity, like if you look at this next example that we're going to do, we've got the derivative of log base a of a quantity, not just x. So that requires chain rule, right? So if we do u substitution, for chain rule, we would have 1 over u ln a times the derivative of u. So one more time, for chain rule, if I use u substitution, I'd have 1 over u ln a, but then I would need to multiply that by the derivative of u. So derivative of outside times derivative of inside. All right, so if we let our 2 plus sine x be u, then we can go through and say this is a and this is u. So it's just an issue of following our formula. We said for chain rule it would be 1 over u ln a times the derivative of u. So let's do that. 1 over u ln a. So 1 over u ln a. And then we need to multiply by the derivative of u. So what's the derivative of 2 plus sine x?
Cosine.
Positive cosine x. And not really much simplifying we could do here. I guess we could say 1 times cosine is cosine and put that in the numerator. But then we've got our answer. Unless they ask me for a decimal approximation for ln 10. But typically we want the exact value instead. All right. Then they give me the derivative formula and the integration formula for a to the x, our exponential function. Okay, so if we've got derivative of a to the x, that's a to the x ln a. And if we've got the integration of a to the x, it's going to be a to the x divided by ln a. Derivatives and integrals, inverses of each other, kind of makes sense. Over here we're multiplying, over here we're dividing. So it's an easy way to help us keep it straight. All right, so let's look at 13. For 13, we've got the derivative of 10 to the x squared. So again, when I'm looking at this formula, this is a plain x. This is not a plain x, so I'm going to need to do u substitution. I'm going to need to use chain rule. All right, so let's let u be equal to x squared. So if I come over here and follow my formula, for chain rule, it would be a to the u ln a times the derivative of u. So a to the u ln a times the derivative of u. If u was x squared, then the derivative of x squared is 2x. So again, if this was our formula, if we modify it for chain rule, that's a to the u ln a times the derivative of u. So we said u was x squared, so that'd be a to the u ln a and then the derivative of x squared, so 2x. And again, not really any simplification we can do there. You might want to move your 2x out to the front, like we typically put a constant out in front, but you don't have to. All right, look at example 14. For example 14, we have a definite integral this time. And it's the integration of 2 to the x. So you'll notice that's a perfect match for our formula up here. We don't need to do any u substitution. So we're going to have 2 in the place of a and x in the place of x. So 2 in the place of a, x in the place of x. So our formula then says that it's going to be a to the x over ln a. So a to the x over ln a. Because we didn't do u substitution, I don't need to replace these x's with u's, so I can just leave my original limits of integration. All right, so let's go through and plug in 5. That would give us 2 to the 5th over ln 2. So 2 to the 5th is 32. And then we can plug in 0, so 2 to the 0 over ln 2. So 2 to the 0 is 1. And because we have a common denominator, we could go ahead and combine the 32 minus 1 and get 31. So for your test, we're going to be looking for an answer like this. It'll tell you to give the exact value and not a decimal approximation. So you obviously could throw this into your calculator and it's going to give you a decimal. It's not going to give you this guy. But you could throw it into your calculator and make sure that you're getting the decimal that is the same thing you get when you type this in. That'd still be a way that you could double check yourself. All right, last thing that we want to look at, example 15, is logarithmic differentiation. For example 15, they ask me, take the derivative of what's in green right here. Take the derivative of y equals x to the 3/4 square roots of x squared plus 1 over 3x plus 2 to the 5th. Okay, just think about this for a second, okay? This is quotient, right? So I got to do quotient rule. So I have to say denominator times derivative of numerator. Going to be there a while because the numerator is a product. So I got to do first times derivative of second plus second times derivative of first. And when I do the derivative of the second, it's a quantity under a radical, so I'm going to have to use chain rule for that. And then when I get back to doing the derivative of the denominator, it's a quantity, so I'm going to have to use chain rule for that, right? So I'm going to do denominator times derivative of numerator using product rule and chain rule, minus numerator times derivative of denominator using chain rule again, all over the denominator squared. And then I'm going to try and simplify that thing. Oh, there has got to be a better way of doing that. Remember what caused us trouble before when we were working with a derivative was the product and the quotient, and we had a way to get around that. Remember the logarithms? The properties of logarithms gave us a way that if we had two quantities that were being multiplied, we could break it into two separate pieces that were being added, and if we had two things that were being divided, we could break it into two separate quantities that were being subtracted, and then we didn't have to do all that product rule, quotient rule stuff, right? Yeah, but that was a logarithm, and this isn't a logarithm. Okay, remember that rule that says what you do to one side, you do to the other side is a legal move? Insert a log on each side. I can do that? Absolutely you can. So I'm going to go through, my original problem was in green, I'm going to go through and I'm going to insert a natural log on both sides. So once I do that, now I can break this all apart, right? I can make it three separate pieces. So I could go through and say these two are being multiplied. I'm going to make that two separate logs that are being added. This one was being divided. I'm going to make that a separate log that's being subtracted. In addition to that, I can get rid of chain rule too, because I can get rid of my exponents and make them constants. So if you'll notice, for the x to the 3/4, we have ln x, but we're going to take that exponent of 3/4 and move it out in front as a constant. For x squared plus 1, if I'll write that to the 1/2, then I can move that 1/2 out in front of the log, and I'll have the log of x squared plus 1. And then for 3x plus 2 to the 5th, again, I'm going to move that exponent of 5 out to the front, and I'm left with 3x plus 2. So now let's go through and take the derivative, because that's what they wanted me to do originally, right? The only catch to this is I no longer have y externally in my problem. It's not y equals anymore, it's ln y equals, right? So if I'm going to take the derivative, I'm going to need to take the derivative implicitly because y is on the inside. So remember, for implicit differentiation, you're going to take the derivative of every piece on both sides, and it's going to be the derivative of y in terms of x. So anytime you hit something that's not in terms of x, you have to leave a dy dx in there, okay? So good review for us of implicit differentiation. So if I go through and I take the derivative of ln y, we've already learned that that's 1 over y. But since that y wasn't in terms of x, I'm going to leave a dy dx in there. All right, then over here, bring down my constant 3/4. Derivative of ln x is 1 over x. Bring down my constant 1/2. Derivative of ln x squared plus 1. Remember that when you're taking the derivative of the log of a quantity, you can put the original in the denominator and its derivative in the numerator. So I'm going to put the original x squared plus 1 in the denominator and its derivative 2x in the numerator. All right, bring the 5 straight down, and then same story here. Original 3x plus 2 in the denominator and its derivative 3 in the numerator. All right, let's do a little bit of simplifying here. I want to get the derivative by itself. So if I want to know what dy dx is equal to, I got to get rid of this 1 over y. So I'm going to multiply both sides by y so it cancels over here, and you can see it shows up over here. Also going to do a little bit of simplifying. 3 times 1 is 3. 4 times x is 4x. 1 times 2x is 2x, and 2 times x squared plus 1, those 2's could cancel out. And so that would just leave me with x in the top and x squared plus 1 in the bottom. And then here, the 5 times 3 would give me 15 in the top, and then the 3x plus 2 in the bottom. So here's my answer. However, this is the derivative of y in terms of x. That is not in terms of x. That's in terms of y, right? So I need to go one more step, and I need to replace that. In the very beginning, we had what y was defined as. It was defined as this whole quantity. So I'm just going to replace y with that original quantity that we had, and then you can see this remaining part. So in the textbook, it gives me steps for logarithmic differentiation. And it says, step number 1, take the logarithm of both sides. So that's what we did. We started off with the green problem. We inserted an ln on each side. So step number 1, take the log of both sides. All right. I would insert another step here. And I would say, then take that log and break it apart using the properties of logarithms into the separate pieces so that it's simpler to work with. All right. Then they say step number 2, differentiate implicitly with respect to x. So that's where we went through and we took the derivative of both sides and we did it where it was in terms of x, so that if we had a y, we had to leave a dy dx in there. All right. Then it says solve the resulting equation for the derivative of y. So that's what we did. We solved the resulting equation for the derivative of y. And again, I would add one more step that they don't have listed there, and that is be sure that you replace any y so that you're putting it in terms of x, because remember we had to replace this y right here and put it in terms of x with the original equation. Okay. So in that way, I can take any derivative that would be difficult to find because of a product or a quotient, and I can rewrite it. Going all the way back to problems that we were doing months ago, we could do them simpler in this way. All right, last thing that I've got here for you are just a couple of definitions in regards to E. When we first looked at the natural exponential E, that 2.71828, and then it deviates after that. It is non-repeating, non-terminating, as pi is. But we talked about where it came from this definition of a limit. But again, they just give me 2 different ways here that we discovered E, and a little bit of a discussion about that on page 443. So you don't have to memorize those limits or anything like that. I just wanted to mention them to you. Okay, so here is our homework for tonight on pages 443 to 444. We're doing 5, 17, 23, 29, 31, 33, 35, 39, 43, 69, 71, 73. Challenge 81.